Hi, good morning, good afternoon, good evening, everybody, from wherever you might tune in. Like Roberto said, my name is Yannick Ongena. I'm a Principal Cloud Solutions Architect at Oracle. And today I'm going to present to you how to automate machine learning with Oracle Cloud Infrastructure. So first of all, let me share my screen with you so you can see my slides. And let me give you a quick introduction. So as part of the A-team within Oracle, I work on the latest technologies. And that's very interesting because we can work on the technologies before they hit the market. So we can test them out. We can help product management to fine-tune the product before they go to the customer, so they are very more mature and the customers can benefit from it. Once those products hit the market, then we help the customers adopt these products. And quite often we find very interesting use cases that are not supported in our products. And that's where we come in. We help the customers, we build the prototypes, and we will make sure that they are successful on our products. And if we finished with those products or with those prototypes, then we might transition those prototypes into the product to make our products even better. And that's what I'm going to showcase today. So I'm going to show a use case where our products don't really provide the features for the customers, and we build a prototype for them that maybe in a couple of months or next year, you might see those features into our products. And the use case that I'm presenting to you is all about digital pathology. And what it is about is that the customer is a research institute that focuses on cancer research. And what they do is they take cells and they slice the cells up and they take images of those cells. And each image of those sliced cells range between 10 and 30 gigabytes. And a data set of an entire cell ranges from 25 to 100 images. So as you can do the math, you can see that those data sets are quite big. We can get into 3 terabytes for a data set with images. So these things get quite large, and you need quite a lot of infrastructure for it to make these things happen. And the way that the customer uses these images is quite complex as well. And what we've seen from other customers is that their workflow seems rather similar to other people who are doing machine learning with images. So what is happening is that once they have the images from the microscope, then they need to scale those images. They need to create some masks. They need to do some pre-processing on those images, no matter what those steps are. And depending on the steps of that pre-processing, you need different infrastructure requirements. So for example, some steps will require a high CPU workload. Other steps will require lots of memory, while other steps don't really require lots of CPU or memory. So it would be really good if we can create a pipeline where we can optimize that infrastructure so we can get the most performance out of the infrastructure based on the needs of that specific step. And that's what we built for them. Whenever the pre-processing is done, we go on to the machine learning phase, is where when the images are processed, they're aligned, they're scaled, there are masks applied to them, then they can throw them at a machine learning algorithm. So typically for images, they use neural networks. And neural networks work really well with GPUs. So that's why we provide them with GPU-based compute instances, where they can scale them out. We can create 10 instances with every instance has 1 or 2 GPUs on them, and they can build their neural networks based on it. But with these customers, and I think most of customers will do the same thing, you're not only doing one model. You typically use a grid search to find the most optimized model. And with neural networks, it can take a lot of time. So you want to have some sort of orchestration where you delegate these permutations of your grid search to the different infrastructure compute instances. And that's what we built for them. We built them a tool where they can define their study with the permutations, with the size of the data sets. And then we set up the entire infrastructure and we delegate all the work completely automatic for them, which is really really great for them because they don't have to think about infrastructure. They can focus on what really matters, which is their research. So what is the core of their problem? Which is why they were looking to move to the cloud. So with the pre-processing part and the machine learning, there's a lot of manual steps involved, and each step can infer some errors in it because it's manual and people are not perfect. Because there are a lot of steps as well, the data transfer between the steps is done manually. So again, there could be some errors in between. And because everything is manual, there's a delay between the steps. Some steps can take hours. If their day is over, they can start the next step the next morning. So you lose a lot of time between the steps. And also the resource utilization is not optimized. As I explained in the previous slide, depending on the steps, you need different infrastructure for it. So this is a visual model on how this looks like for them. The white box is their on-premise infrastructure. They have their microscope that is linked to a computer that does the imaging. And then they use a fast data transfer onto our Oracle Cloud. And they use VPN. It's a proprietary VPN called Fast Connect from Oracle, which allows them to connect their data center or their on-premise infrastructure to our data center. So this is really fast. So they have the most optimized data transfer to move all those terabytes between the data centers. Then we store the data sets onto a shared storage facility, and then we apply the processing and the machine learning to it. And as we can see, the pre-processing, the technology or the main technologies we use are Kubernetes, Arco for the pipeline, Python, and Docker. For machine learning, Python, TensorFlow, Keras, Terraform, and of course NVIDIA CUDA in conjunction with TensorFlow for the neural networks. So one of the core things that we wanted to do is infrastructure optimization. And this is not only from a cost perspective, this is also from a performance perspective, because you want to be as fast as possible to get those results out there. So what was unique, or what is unique about a research use case for this, is that there are a lot of variables in play with studies. So every study has different requirements. So we needed to find a solution that could meet all those requirements at the same time. So for example, we could have a step 1, which requires a lot of CPU. A step 2 requires high memory usage. Step 3, which could be, for example, not scalable, so we only need one instance for it. But the other steps could have a massive horizontal scaling, which could drill down the time quite tremendously. And with the cloud, it doesn't really matter if you use a compute instances for 100 hours or you spin up 10 compute instances and you use those 10 for 10 hours. The cost is the same. But in matter of time, you'll divide the time by 10 if you can spread it out over 10 machines. So that's a big win for them, and that's what we wanted to do for them. And what is also important is that the size of the data set dictates how much we scale. So if a data set is maybe, let's say, 100 images, we are sufficient with 2 different instances per data set. But if we have a huge data set with thousands of images, then of course we want to scale out much more. And this is also what our solution provided with them. And the beauty of the solution is that especially the container-based architecture that we proposed or that we built for them is generic. And we haven't built anything proprietary. We haven't built any line of code. So this solution could be perfectly usable for you if this use case also fits to you, because there's nothing proprietary in this. So what the solution is about is that it's container-based. So it runs on a Kubernetes cluster. What this means is that, of course, your code needs to be in Docker containers. And that was problematic for them because I don't know how it is with different research institutes, but for them, using Docker was new for them. They were proficient in Python and all the tools required for their machine learning, but they didn't really have the know-how when it came to containers. So we helped them, and it was fairly early on that they noticed that transferring their code onto a container is fairly straightforward, because typically these are scripts, and scripts can be run from a shell. So those lend themselves to be migrated onto a container very easy. So that shouldn't be a problem if you want to adopt a solution like this. What is really beneficial with a Kubernetes cluster is that within a cluster you have worker nodes, and a worker node has a pool of workers attached to it, and this basically dictates what infrastructure you're using. So because each step requires different infrastructure needs, we could create worker nodes with their pools depending on those steps. And then within the workflow, we could assign steps to specific worker nodes so that they are assigned to the optimized infrastructure. One drawback we have at the moment within Oracle is that our worker nodes on Kubernetes, we do not support GPU. So for the GPU workload, we had to come up with a different architecture, which I will explain later on. But for now, this is focused on the data processing, the pre-processing. And this could also be used for example, for algorithms that are CPU intensive. So not really neural networks, but other algorithms like typical regression models could be done on this as well. Then we use Arco for pipeline management. And Arco is an open source tool which runs on OKE, and it allows you to build a pipeline. And within that pipeline, you define the steps and the worker nodes that are attached to those steps. And then it will scale out to its infrastructure. And whenever those steps are done, it will start the next steps. And what is really good for Arco, which is really suitable for data science and for machine learning, is that you can also specify that each step depends on the previous step. Also when it comes to input and output. So Arco knows how to pass the output of a previous step to the input of the next step, which works really well for this case. And because we work with images, one of the really important things to provide performance is that we need to have a really fast storage solution. And we chose to use Cluster FS, which is also open source, which you can deploy. And we chose to deploy it on bare metal instead of on virtual machines. And the reason for this is that on Oracle Cloud Infrastructure, bare metal shapes have two physical network interfaces. And that is really important to provide that performance, because the internal communication between the cluster FS nodes happens on one specific network interface, and the communication to the outside world happens on a completely different internet interface. So the traffic is not limited because of this, because you get full bandwidth specifically for the output, and this gives us really good performance for the file system, which is really important if you work with images that are gigabytes of size and data sets of terabytes. And within the Kubernetes cluster, we use persistent volumes that can be shared between the pods. So that's why they can communicate the input and output between each others. So that helps with the data management between the steps. So this is a quick overview of the architecture, how it looks like. So as you can see at the bottom, those three blocks, those are the cluster servers running on bare metal, where the communication runs between a specific interface card. And then at the top, we have our OKE, which is Oracle Kubernetes Engine, which is where Arco runs, where we have the pipeline running. And on the right-hand side, you see OCIR. This is our internal registry, where we register the Docker containers so they can be consumed by our Kubernetes engine. So that's where the customer is deploying their Docker containers too. And these are also versioned, so you can easily specify the version and manage it. So this is an example of the Arco dashboard. And as you can see, each in the middle, this is the specific step. So we start, then we have a scale step, which is, it scales the images, and this is horizontally scaled within the Kubernetes cluster. Whenever this is finished, it will start a masking step, which is also scaled. It will execute another step, and then here we can see that there's a calculate step, which we cannot scale because the process itself needs the entire data set to work on, and we cannot, the process itself doesn't lend itself for scaling, so we need to run it on a single worker node. And this can all be defined within Arco, so this is really flexible. And then we do the last step, and as you can see, this can be scaled out again. So this is really optimized, and it works really well for them. The definition of this pipeline is similar to OKE. It's YAML based. So if you're familiar with Kubernetes, then it's straightforward to get into Arco as well to define the workflow. So the next part is the GPU part. So like I said, at the moment we do not support GPU shapes to run on Kubernetes. So because the customer want to have their neural network in, they want to run it as a grid search to find the most optimal model. And on the right-hand side of my slide, you can see these are the different permutations that we want to run through. And the thing with neural networks, as most of you probably know, is there's a lot of randomness involved with it. So we want to run these permutations at least 3 times or even 5 times to rule out randomness. So because of the time required to run each permutation, it takes a lot of time. And we want to scale out as much as possible. And in order to do this in an optimal way, we need to have some sort of orchestration between those steps. So that's what we did. We created a master script for them, which is a multi-threaded process, which keeps track of the different worker nodes. So what happens is that we provision the infrastructure based on Terraform. And then we delegate permutation to the different instances that we have. We do this by SSHing into the different worker nodes, and we execute the neural network. And we monitor the output of it. And when it's finished, we know that we can send it a different permutation. So if we have 10 different instances, we can do the 10 permutations at the same time. Whenever one permutation is done, it will kick off another one. Whenever all the permutations is done, we know this because we keep them in a queue, then we tear down the infrastructure and everything is destroyed. So all the infrastructure involved in this is temporarily. We do not keep anything. In order for this to be really workable, what we do is we create a custom image. And a custom image is, we first create a VM, a compute instances, where we install all the necessary software. We install Conda, we install TensorFlow, the correct version of TensorFlow with the CUDA drivers, and then we create an image out of this, so that when we create new compute instances from within Terraform, we use that custom image and we know everything is installed. So we know everything will work. And then the code is stored into GitHub. We clone that repository using a command in Terraform, and everything is sorted out, and then we know we can be ready. So this is basically how it looks like from a high-level perspective. So we have a compute instance, a virtual machine that runs the master script. And then we have the different virtual machines which are standing by to receive the permutation information. And when they receive the permutations, they send data back to the master script, so it understands when it's finished. When all the permutations are done, when the queue is empty, then the master script will also do an aggregation of the results. So the script that we're using to create the model also execute or outputs a status file that tells us how long the execution took. It tells us how good the model is based on the test data, and it gives us some more information about the model itself. And then the master script will aggregate that data into a CSV file so that the customer can look into it and try to find what the best model is after everything is run. So what are the benefits that we see from the customers that when we implemented this? So this solution has been implemented, it's done, and they started using it. And what we saw is that for the pre-processing phase, so that's the Kubernetes part, which is containerized, typically what they had before on-premise, a data set took on average 23 hours. And when we executed the pre-processing phase on our cloud with our solution on the same data set, we noticed it took only 13 hours. So that's a huge benefit. It's almost half the time. Plus, everything is automated. So there's no delay between the steps. If there are 20 steps involved in that workflow, then there's no manual, there's no person who needed to execute the next step. So in real time, the time gained is even more, because it took 23 hours of execution. But if there's a night in between, the workday is done, then yeah, you'll basically are 10 hours away from office or longer, and you're just waiting there. So that's an additional gain. For the GPU workload, we saw an even increased or even better performance. When the data set was executed on premise, it took it took on average 19 hours. While when we execute it on our cloud, it takes 5 hours. And those numbers are basically only from half of what they expect to use. So the biggest benefit that they see is because of the scaling. The more we can scale, the more time they gain. So if we can double the infrastructure for the pre-processing part, we could get to probably 6 or 7 hours. If we can double it for the GPU workload, we can go to 2.5 hours. And when it comes to cost, that really doesn't cost anymore, because you pay for 5 hours of maybe 10 instances. But if you go to 20 instances and it takes 2.5 hours, you pay the same amount of money. So it's really a great benefit for them. What we also see is that there's a really good optimized usage of the resources, because all the infrastructure is optimized based on whatever needs to be done for that workload. And it's really easy to scale. It's just a parameter of it's even autonomous, the scaling with Arco. And there's a big reduction in human error, because everything is automated, which is really good. So yeah, that's my use case that I wanted to present. It's really useful. Most of it is it's not proprietary, so everybody can do this on basically any provider. It's not proprietary to Oracle. We use a lot of open source to make this happen. So I hope I inspired maybe some of you who have similar use cases to try to implement something similar. So I hope you enjoyed, and I think we can open the stage now for a Q&A.
Well, in fact, that was a very wonderful presentation. Thank you so much, Yannick. I am 100% sure, and as I said before, I am super sure that everyone was glued to the screens, that we're just waiting for this opportunity to start asking you all their questions and everything that they have on their minds. So once again, I'd like to invite you to your very own DSGO Q&A, live Q&A. The way it works is that the attendees will send questions through the chat, and I'll receive them here, and well, I'll then ask them to you. So how about we start opening the floor for Q&A? Okay, we have one question coming in. The question coming in from Alex. Alex is asking, okay, Yannick, I was wondering, how did you get started in this whole world of data science?
It's quite interesting from my perspective, because I'm not trained in data science or machine learning. But the nature of our job basically asked for it. Within the A team, we always worked with the latest technologies. And we noticed that data science and machine learning is really a booming industry. So that's why within Oracle, we started developing our data science platform. We took over datascience.com, I think, and we needed to have a team that supported this. And I was always fascinated and interested into statistics and robotics. I built my own robots before. So for me, it was a natural transition to support data science within Oracle.
Okay, great, wonderful. We have a question coming in from Pavan. How different is OCI from GCP or AML?
Different, I don't really know if there's a big difference. We try to be open, and I think the other providers try to be open as well. So when it comes to the core Kubernetes engine, they're fairly similar because once you try to put something very specific into it, you start to have proprietary stuff into it. And that's not really easy for people to move around because we see a lot of customers with hybrid solutions. They're customers with both with us, with Amazon, with Microsoft, and they want to have the same solution deployed on all the clouds. So we need to be really open. And that's why you'll see all the similarities between the providers, because otherwise it's not really easy for customers to deploy the same solution on the different clouds.
Okay, great. We have also another question coming in from Vikram. Vikram asks, is it possible to run multiple processes at once?
Yes, that's exactly what we basically support and we do. So what we call, well, I don't know, the definition of process can be quite difficult, so I don't know what he means with process. I'll assume with process he means study. So for example, we can run multiple studies in parallel where we assign different infrastructure compartments to each study, so that each study can run at the same time. Yes.
Okay, great. Well, wonderful. Vikram, I hope that answered your question. If you have a follow-up, feel free to post it. We have another question coming in, if you give me a second. We have Naman Sharma asking, what's the difference between pipeline and assembly line?
Between?
Pipelines and assembly lines.
I don't really have an answer for that, to be honest. With pipelines, I would say that a pipeline is something where you have multiple parts that depend on each other. But I don't really know how to distinguish from an assembly line.
Okay. Another question coming in, this time from Miguel Garcia. In which cases might it be better strategy not to use cloud solutions but on-premise?
First of all, I probably think the privacy, security of your data might be a concern. But in those cases, a lot of the cloud vendors provide specific solutions to cater for that as well. Some other things that might be viable if you have your data on premise and there's a tremendous amount of data that you need to stream that is not really feasible to move them to the clouds, then I would say it's also viable to have your solution on premise. But the problem, or the big advantage that we see with the clouds is like I explained, we have that scaling capabilities. I mean, on premise, you cannot really say, oh, I'm putting 10 nodes in it. In the cloud, it's very easy to scale.
Okay, well, wonderful. I think that's all the time we have for today for the Q&A. That was a great presentation, and I think an even greater Q&A. Thank you so much, Yannick. Our audience was psyched and was super happy to have you here. They were super engaged, and the questions just kept on rolling in. And to the audience and to the attendees, I hope you all got a chance to pick Yannick's brain with this Q&A. Well, once again, thank you so much, Yannick.
Thank you.